Do you want to know how to build a low-friction launcher?
Yeah!
Well, secrets will be revealed.
Okay, let's look at this prototype. This has 3 axles, and it has 60 to 12 and 36 to 12. This means that 1 rotation of this axle results in 15 rotations of this axle. Now let's look at a diagram. First thing you need to know about a motor is the max torque and the max angular velocity. For a force motor, the max torque is 15 inch-pounds. For angular velocity, the max is 100 rotations per minute. Now, this is a 5-to-1 gear ratio. So what you have to do is you have to divide the torque by 5 and multiply the angular velocity by 5. This leaves you with 3 inch-pounds and 500 rotations per minute. The second stage is the 3-to-1 gear ratio. What you have to do here is you have to divide the torque again by 3 and multiply the angular velocity by 3. This leaves you with 1 inch-pound and 1500 rotations per minute. Now let's say you have a friction of 0.5 on this axle. It might not seem like much compared to 15, but it's actually 50% of all the power your motor produces. I know what you're thinking. So it's 50% is being lost. We still have another 15. That's okay, right? No, it's not, and I'll show you why. See, if the friction's at 50% here, then your speed will decrease by 50%, leaving you with only 750 rotations per minute. Now, ideally, you want your friction to be as close to 0 as possible. You want all the energy in your motor to be dedicated to launching balls. And according to the efficiency curve, you want your efficiency to be somewhere around here. Some people may wonder, which motor is the most powerful? Is it force, speed, or turbo? The answer is none of the above. All the electrical parts are the same. The only difference is the output gears: force, speed, and turbo. They all have the same power, which equals 1500. Only force has 100 RPMs, speed 160, and turbo 240.
In physics class, we learned that the kinetic energy of a ball with the mass of m flying forward with the velocity of v is equal to mv squared over 2. Similarly, the kinetic energy of a flywheel with the moment of inertia, or I, rotating at angular velocity omega is equal to I times omega squared divided by 2. Knowing that, you can answer the question: where do the balls get their kinetic energy? Well, the answer is uranium. Our local power plant burns uranium, generating electricity, which we use to charge our batteries, which we use to run our motors, which we use to run the flywheel, and the kinetic energy stored in the flywheel was what we used to launch the ball. Then, when the flywheel launches the ball, it slows down, losing some kinetic energy. That energy goes into 3 places. Some goes into accelerating the ball, some is lost to the compression of the ball, and the rest is lost to friction in the flywheel bearing. So, there you have it. The energy flows all the way from the Big Bang to the high goal of the Red Alliance.